This is the Pearson Edexcel Further Mechanics 1 paper from June 2020. So it's based on this book here. I'll say on the record, I've actually legit never taught mechanics at A-level, either certainly not further mechanics, but even regular mechanics at A-level. So this is all entirely based on 10 to 12-year-old memories of doing mechanics at school. I did A-level maths just 12 years ago, and we did the old course, the modular course, and I am the only person, along with, of course, my brother who was in the class, the only other person in the class, and I'm the only person aside from him that I've ever met who did M4. So there were 4 mechanics modules on offer, and I did all 4 of them. Never met anyone else, not in that class, who did that. So yeah, I've got vague memories of doing lots of mechanics. Let's see how this goes. A lot of this is just me figuring it out as I go along, rather than being professional and actually knowing what I'm doing. So an impulse is MV minus MU. You're allowed to use vectors in here if you want to, so I've just made them bold to signify their vectors. M is 0.5, this is U, this is V. We can just multiply these things out and collect them, so minus a half minus 2 is this, and then 3 minus 1.5 is that. So that's our impulse. We're looking for the magnitude of the impulse J, so we just do this squared plus this squared square rooted, and we'll get this answer here. So that's a nice, easy start. The angle between the direction of the impulse and the direction of motion of P beforehand is alpha, find alpha. So let's just very quickly draw it. Beforehand it's going at 4, 3, which is like this way. Afterwards it's going this way, minus 1, 6. The impulse is therefore sort of in this direction, and we can see that here, right? Minus 2.5, 125. Sorry, 1.5. And there's lots of ways you could do this. You could dot product these and do the cos theta equals dot product over the 2 magnitudes if you want to. I think I do that later in the paper. I just chose to just do lots of different things all the time to kind of show off all the different things you can do, but I just did some regular triangles here. So this vector means it's going 2.5 across for every 1.5 it goes up. So I can do some tan inverse of this over this to find this angle here, which is that. So that's that angle. And then I can do a different triangle here. I can say this is, this is 4 across 3 up, isn't it? So that's 3 up here and then 4 across there. And I can do tan inverse of 4 over 3 to find this angle. And then I can add those 2 results together, and I'll have all of this angle, which must be the angle between the impulse and the original direction. So just add those 2 results together, and we'll get this answer of 112, roughly there. Good, so that's question 1 done. This is question 2. Going to ignore the second half for now, because it involves a different picture. Shout out to Dr. G, Dr. Griffiths, my mechanics teacher for all 4 of those modules, because he taught me how to draw things. So here's a truck, and here's a road. That's how we draw things in mechanics. The truck weighs this much, so I'll put that in there. It's got a driving force, a driving work of 25 kilowatts. Now that's not a force, so we're going to have to change that into a force later. The resistance is this, and that is a force. So I'm going to need to change this. Now power is equal to force times velocity. So to get this into a force, we're going to need to do the power, which is 25,000, divided by the velocity, which is 25, and we'll have our driving force of 1,000 newtons. And this we can also substitute in 25 to find the resistance when you're going 25, and all we have to do is F equals ma. The force forwards is 1,000, the force backwards is this with the 25 in it, so do that minus that. And of course ma is just m times a, which is what we're looking for, so we work this out, we divide by 1,200, and we get, is that 1,200? Yeah, it is. And we get this as our deceleration. Good, and then B, or part B, is on a slope now. So if you're a mathematician and you don't love inclined planes, you're not a mathematician, because inclined planes are incredible. I hate mechanics, which is why I've never really taught it, but inclined planes, mate, they are exceptional. Here's a slope now with the same truck on it, and the inclined plane has an angle of sine theta is 1 over 20. Now, you can, of course, inverse sine 1 over 20 to find the angle. Just know that if you ever do that, I think less of you. Because what you should be doing, if you ever see this, is saying you've got a triangle here with opposite 1 and run across 20, right? So you've got imagine a little right angled triangle in here with opposite side 1 and, hypotenuse, I should say, of 20, isn't it? Opposite over hypotenuse. So little triangle here, 1 is the height, 20 is the hypotenuse, which means that if you imagine that triangle, you can do 20 squared minus 1 squared to get root 399 along the bottom here. And so cos theta is root 399 over 20. And tan theta is 1 over root 399. You don't need to know this, by the way, for this question, I don't think. But this is how you should do it, and I'll do it like that later on in the question as well. Or later on in the paper, I should say. Anyway, we've got a time when the speed is v, I guess. Direct magnitude of resistance is still this, fine. The work is still that going forward. So we've still got to manage to do that. Now, we've got a speed here of v, so notice to get a force going forward, I did this divided by, I think it was 9 before, didn't I? Was the speed 9 before? Sorry, the speed was 25 before, so I divided this by 25. Now, to get the force forward, I'm just going to divide it by v, right? Because v is the speed, big capital V. So the force forward is 25,000 over capital V. I'm just putting that in there. And the force backwards is this, again, when v is big capital V. But the only other thing we have going on here is we have an mg going straight down. So this is 1,200 g going straight down. And then we can break up this triangle. This is, of course, theta. You can do a little bit of similar triangles to show this is theta, which means this length here is mg, 1,200 g cos theta being this. And this across is 1,200 g sine theta. And sine theta is that. We can, of course, simplify to that. And so now we have two forces going down the hill. We have this one here, which is gravity, and we have this one here, which is the resistance, and we have this as our driving force. So therefore, setting up F equals ma, we have the driving force minus these two forces is equal to ma. But a, of course, is 0 because we're going at constant speed. So therefore, we can actually just say this force matches the other two, and we could just say that straight away. So we can say this force matches those two. In other words, I've just substituted 0 into there, got a 0, and then just moved the other two forces onto the other side. You can do it like that if you want to, but yeah, we get this. We times everything by v, and then we can rearrange a little bit for this, I think. We can rearrange some more. You can type this in using g as 9.8. I assume it probably told you to use maybe at the top of the paper or at the start of the question, I'm not sure. And you get this, and then we solve that in a calculator and we get this, and that will be our answer. Good. Question number 3 then, two particles, 3m and 4m. So here's the 3m particle going at 2u, and the 4m particle is in front of it going at speed of u. So clearly these things are going to collide at some point because this one is going faster, it's catching it up. So they're going to collide, and after they collide, I'm going to say that this one has speed v1 and this one has speed v2. Right? And now it's questionable whether or not when they collide, I mean, this one is definitely still going to be going in this direction. But we don't yet know whether this one is going to be going in this direction but slower forward, or whether it's actually going to turn around and go backwards and this will be a negative velocity. I don't know that. It's actually asking me to sort that out, right? It's asking me to show that they're both still going in this direction. So that's what we're going to show, and the coefficient of restitution is e. Now, we've got a few things to do here. Let's do the balance of momentum first. So mass times velocity plus mass times velocity is equal to mass times velocity plus mass times velocity in the second situation. So we get this. So that's one simultaneous equation, which is very useful to us. I've just cancelled all the m's, obviously. And now the second one we can form uses this e thing. So we've got this formula for e. The speed that they separate at divided by the speed of approach is equal to this coefficient e. So let's put that in. So the speed they're approaching is clearly u, because 1 is 2u, 1 is u. And the speed of separation is just this one minus this one, so v2 minus v1. So we have this, we times across by u, and that's our second simultaneous equation. So I think we can solve these. I'm just going to put this one here. I think if I times this one by 4 is probably what I did, and then add together, no, sorry, then do this one, take away this one. I think I'll get that. Yeah, that seems good. And then these are the two original ones. If I instead, because that way, now I've got v1 there, if I try and get v2 now, by timesing this one by 3, and then I'll add them together, I think I'll get this for v2. Good. Okay, and now, so that's v1 and v2 in terms of u and e. Now, e is a number between 1 and 0, so it's definitely positive. U is positive because it's going in this direction, and I've just arbitrarily chosen this direction to be positive. So we assess these and go, okay, clearly v2 is positive, like trivially positive, right? Everything here is positive. And I said that before, didn't I, that this one is clearly still going to be going in this direction. Now this one, if e is at most 1, the least this can be is 6u, right? And so that's still positive. So these are both still going in the same direction, and maybe just briefly write down what I just said there to make sure. I actually think part B is a little bit more tricky. So after the collision with A, B then goes forward some more and collides with a third thing, C. So and C is at rest. So C is just sitting here, and it gets slammed into by this second particle B, and then eventually, of course, and that means that C is going to be shifted forward. It's going to have a new velocity v4, I've called it, and B is also going to have a new velocity, which I've called v3. And now we're being asked to show, by the way, the coefficient is the same as it was before, and now we're being asked to show that A and B, which is this particle and this particle, are going to collide again. Now, there are a couple of ways for that to happen. Obviously, if particle B turns around, then they're definitely going to collide again. However, it can also just be the case that B is slowed down such that V3 is less than V1, and therefore this particle catches up with it again, just like it did before. So really what I'm aiming to show is that V3 is less than V1. If it's so much less that it's negative, then great, then it's going to turn around and slam into it. But I just want to show that it's less than V1, and therefore V1 will catch it at some point. So that's the aim, and we actually do something very similar to get this, right? So we use the same formula I did before, where the approach speed was clearly V2, and the separation speed is V4 minus V3, that still equals E. Conservation of momentum again, so V2 times 4m, this one's going at speed 0 or velocity 0, so that doesn't count, and then likewise here, so this is conservation of momentum here. Obviously expand that out and expand this out, and we get again two simultaneous equations. So this is very similar to part 1, I guess. It's a little bit more tricky to solve these. We've got to times this one, I think. I think I times it by 2 everywhere, and that meant that I could cancel or get rid of the V4s, because like I said, I'm not really interested in V4, am I? I'm really interested in V3 and V1. I have an expression for V1, which is going to be helpful, but I'm not interested in V4, so I'm going to double all these and take away. I think I'm going to do this one, take away this one. Yep, that's what I did. Good. I think I can factorize out the V2, I think, and divide by 6, I guess, just because why not? And that's my V3. And what I'm aiming to show is that V1 minus V3 is positive, right? Because I want this speed to be bigger than this one. So what we do is we assess, sorry, by the way, V3 is not very helpful if it's in terms of V2. So what I can do is I can put this expression for V2 into there, by dividing by 7 and then putting it in there as well. And now I just have V3 in terms of U and E, which is great, because now I can consider V1, which again I'll divide by 7 to find V1, minus V3, and I'm aiming to show this is positive. So okay, we just do some expanding out. I factorized out the 1/7 because I didn't want to deal with it. We put that all together. There should be a closed bracket somewhere in there, but I think you get the point. We put it all together. We can keep kind of expanding, and I think at this point, at this point I just times everything by 21. Technically I should say this, yeah, this is a mistake. There should be a 21 brackets here, because I times everything by 21 here. It's not really going to make a difference, because all I need to assess is whether or not this is positive, and if this is positive, then when I times it by 21 it will still be positive, right? So yeah, let's just pretend I wrote a 21 brackets there, and just say it's fine. I just need to show that this is positive. And to do that, of course, it's just a quadratic, so I can just, I chose to differentiate. You don't have to do it this way. Set it to 0 and solve, and you get that its turning point is at 3/4. Do you, though? Or do you not get its 4/3? Oh, I've completely messed up this question, haven't I? Just completely messed it up. I think I was thrown off, well, I wasn't thrown off here, I just didn't notice it. But I've completely messed up this ending. This would totally solve for 4/3, and then when you put in 4/3, you find it's a positive number. And if it turns at a positive number, I mean, it's a quadratic that just looks like this, right? But if it turns at a positive number, that's its minimum. Of course, this isn't its minimum because I've completely messed this up. But the idea is good, right? That's what matters here, is it's the thought that counts. The thought that I had was good, I just executed it poorly. But anyway, I've shown that this thing is always positive, I think, if I actually did it right. And therefore, V1 minus V3 is positive, which means this is going faster than this, which means they'll meet again. And just briefly explain that at the end. Yeah, but sure, messed that up, don't really care. Let's do question number 4. So we have a wall here, we've got a particle going in and then a particle going out. Good, we've got a mass of 0.5 is the particle here. So we're actually going to do something very similar to question number 1. I'm going to talk about the impulse, which is mv minus mu. Just put those in with the mass. It's actually just the same thing we did before, isn't it? And we get the impulse as this. Now, the impulse, we just need to know, acts perpendicular to the wall. So 90 degrees to the wall. Now, if they've given me this, so I'm allowed to just kind of use it. If I just do this, dot this, it equals 0. And so therefore, this is perpendicular to this, which means the wall is parallel to this. And I did check the mark scheme. I'm just allowed to get away with doing that. So I don't have to show this from scratch, but I can just get away with using it. So that's quite cool. Next part then, show that E, or find the value of E, sorry. So okay, there's a number of ways you could do this as well. What I chose to do, you could do it very similar to question 1. You could get out some right-angled triangles and do some trig. But what I chose to do was dot product this and this, and then divide by the size of the magnitude of each vector, and that's the definition of, or the dot product is this is the definition of dot product, just rearranged a little bit. So this dot this, and then divided by, so 7 squared plus 2 squared is 53, and then 2 squared plus 3 squared is 13, just in case you didn't know where I was getting those from. And that will find me this angle here. So I'll just do that, and I'll find this angle is that. And I can do exactly the same here. So I can find the dot products between this and this, divide by their respective magnitudes, and I'll find this angle here. And what my plan then was if you have these two angles, you've got this formula for the coefficient of restitution, which is tan beta, the angle that you leave on, divided by tan theta, the angle that you enter. So I can just do tan of this divided by tan of this, and I'll find the value of V is that. And it didn't say that I had to do this like exactly or intelligently, so that's how I did it, just with rounding numbers. It's mechanics, isn't it? So we don't have to be precise. It's just mechanics. Who cares? Cool. Question number 5. I think there are only 7 questions, so we're getting through it, and we've only found 2 major mistakes so far, so I'm going to count this as a success. A smooth uniform sphere is 0.3, and then another one, mass 0.2, so obviously we're going to draw it. One is moving at this velocity, and the other is this velocity, so it's going in this direction, isn't it? Minus 3,1. And they have this is important, they have, the incident of collision, the line joining their centers is parallel to I, so it's a horizontal line joining the centers. Now that's important for a couple of reasons. The vertical component of the velocity is preserved if they meet horizontally like this. So when we're thinking about the outward vectors that these things leave on, the vertical component is still going to be 2 for this one, and the vertical component of this one is still going to be 1, or 1j, I guess. So that's kind of important. And then what I really want to talk about is, firstly it's saying kinetic energy, which is a half mv squared. We'll use that a couple of times, I think, in this video. Of q halves. So it's kinetic. So we can find, obviously, we can find the speed here, or v squared, I should say. I should have just put v squared and not this square root, but it does not going to matter, is it? So yeah, that was pretty dumb. But anyway, so 3 squared plus 1 squared is 10, so we can just put a 10 in as this v squared, and then times a half is 5, and times that is 1. So the kinetic energy to start with is 1, which means it must leave with kinetic energy a half, because it's double what it was. So if it leaves with kinetic energy a half, I think I can solve that, because if I call its horizontal component AI, I can say that a half, which is its new kinetic energy, is equal to half times m times its new velocity squared. Of course, I can get rid of the half and the 0.2 to find this. And so v squared is 5, but I know the vertical component is 1. So 1 plus something else squared is 5, and I think that something else has got to be 2. So it's going to be traveling this way with velocity 2, with horizontal component of 2i. Now, the thing I should say here is that this could be a minus 2, of course. And I'm going to deal with this at the end of this question, not right now. We're just going to run with this for now. So okay, I'm going to say this is 2 across, this is 1 up. So I'm done here. Now let's find the horizontal component of the other sphere, this one. And to do that, I'm going to talk about conservation of momentum, but I can do this just in the horizontal plane, right? So I can just say that 0.3 times b plus, this is after, isn't it? 0.3 times b plus 0.2 times 2 is equal to before, which is 4 times 0.3, and 0.2 times minus 3, because that's going in the other direction, of course. And we can solve for b, and we'll get that b is 2/3. And so this is 2/3, and this way is positive to the right. Basically, I'm taking to the right as positive for all of this, but it's going 2/3 this way. So yeah, velocity of this is 2/3 2, I guess, and this one is 2/1, I guess. Yeah, that makes sense. I think I've got that okay. I'm just checking for mistakes. I think I'm getting paranoid. The coefficient of restitution between P and Q is what I'm supposed to find. So we just do speed of separation divided by speed of approach. Again, we can just do this horizontally. So the speed of separation is 2 minus 2/3, and the speed of approach is 4 minus minus 3, which is positive 7, and we get E is 4/21, I think. Now justify my answers. Now I think what this is, and carefully it says even, I think this is what this is getting at, is the issue I had up here, where I could have chosen A to be minus 2. In other words, the ball goes this way, speed 2, or this way, speed minus 2, as I've written there. Now the problem with doing this is when you try and find B, which is the horizontal component of this one, and you do exactly the same thing, you use the conservation of momentum, put in a minus 2 in for this one instead, and what you find is B is 10/3, which initially seems okay until you realize, well, okay, that's 10/3 going this way, but minus 2i means this one is going this way. And so the two balls have sort of passed through each other, right? This one's continued going this way, and this one has continued going that way. And that doesn't make any sense. So this minus 2 doesn't make any sense. The balls would pass through each other. So therefore, I think I'm happy to say that my first thing that I did is actually correct. And we have all this. Find the size of the angle through which the direction of motion P is deflected by the collision. So it used to be going at 4, 2 this way, like this, 4, 2 this way. And now it's going at 2, 2/3. So 2 up, 2/3 across. And I think the angle through which we're deflected is going to be the difference between this angle and this angle, right? So like if this angle was 30 and this one was 50, it would be deflected by 20 degrees, right? 50 minus 30. So, or 50, yeah. So let's do tan inverse of 2 over 4 and tan inverse of 2 over 2/3 and just take away our answers and we'll get 45 degrees exactly, I think, which is quite nice. And also suggests that there wasn't a prettier way of doing it, but I don't really care. Question number 6, we've got a string. This is always an interesting question. It's about an inclined plane again, and but this time you've got a mass on a string, and the string starts off very loose, right? Because the mass is sitting on the same length, at the same place as it, and then you push the mass upwards, and the string kind of follows it out and stretches out a little bit until it stops and then comes back again. So that's kind of what's going to be happening here. Again, we've got tan theta is 5/12. You should know the 5, 12, 13 triangle. Again, imagine 5 here, 12 here, so therefore 5 squared plus 12 squared is 13, so sine of theta is 5 over 13, and cos of theta is 12 over 13. We should be able to get that, I think. Good, so it's initially held at A, and then its projected speed root 6gl upwards. So okay, lots of things to do here. Mu is a quarter, and this is the finishing situation, right? It's projected upwards, and the string is going to be taut here, and stretched as well, because it's a stretchy string. It's going to be stretched out here to length 3L. It was length L, so it's going to stretch by quite a lot until it stops, and we're just discussing this to start with. Show that K, which is this number here, which is to do with the modulus of elasticity, is this value here. So there's a lot to do here, I think. The first thing I did was, just finish off the picture, I guess, mg obviously downwards, and then we've got mg cos theta that way and mg sine theta that way, which is going to be these values based on what I set up here. So that's mg cos theta, mg sine theta. And we've got a reaction force, obviously, which is mg cos theta. And therefore our friction, which is going to be acting this way because we're projecting this way, is going to be mu r, which is going to be this here, and that force is going this way. Okay, and now that force is going to act for a distance of 3L. So work done is the force times the distance it acts over. So we have this, and that's the work done in total. And what I'm going to be planning to use here is the energy work equation. So I'm going to have the work done equals the total loss of energy. So that's my work done bit. And now I need to figure out all the changes in energy that are going on. So we have lots of different energies going on here. We have a potential energy because the height of the thing has changed. Now, how much is the height changed by? Well, it's changed by 3L sine theta. This would be, of course, this, you can do some Salvatore if you want. This is theta. This is going to be 3L sine theta. Of course, sine theta is that, so times by 3L and you get that. So that's the height change. So the change in kinetic energy, in potential energy is mgh. So mg times the height difference, which is this. That's the gain in potential energy. The gain in elastic energy, now the elastic energy equation is this. And lambda is this kmg object. X is the amount that it stretches by, and it's not stretched by 3L, it's stretched by 2L, because it naturally sits at length L. So X is 2L, and then we've got a 2L at the bottom here. This becomes 4L squared, cancels with the L, cancels with the 2, and you get gain in elastic energy of that. Now there is also a loss in energy, of course, and that's because it's initially got speed of this, and here has speed of 0. So our loss in kinetic energy is a half mv squared. This, of course, squared is just 6gl, and then there's no speed at the end. So this is just the loss in kinetic energy. And again, I'm going to use the work energy equation here. So I'm going to say that the work done, which I worked out to be this earlier, is equal to the total loss of energy, which is my kinetic energy minus the gains that I make in potential and elastic. So I have this equation here, I think. Cancel out the mgls, obviously, and we solve for k, and we have our answer. Good. Find the acceleration of the package the instant it starts to move back down the plane. So it's stopped here. It's got a string here which is stretched as much as it can, or as much as it's going to, I guess, in this scenario. This time I've got a force acting up here, which maybe I should have animated in. But this is, if you recognize it, good. This is the frictional force. This is the maximum frictional force that I worked out way back here. Because this time, of course, if the thing is coming back down the plane, the frictional force is going to be acting this way. So we've got a force this way, and the force heading downwards, we've got a force heading downwards of this one already, remember, mg sine theta, that's gravitational force pulling it down. And we have one last force of t, which is the tension in the string as it wants to relax back down. And this is how we find the tension in the string. It's lambda, which is just this, and of course we already know k is that, times the stretch, which again is 2L, from L to 3L is 2L. At least the instant it starts to move back, that's what the stretch is. And then, of course, just an L on the bottom. So we put in all those values, and we get the tension is this. So that's the force at the instant it starts to move back. That is going to decrease immediately. But at the instant it starts coming back, that's the force coming back. So we just have three forces here. We have the tension coming back, the gravitational bring it back, and we also have the friction going the other way. So we say F equals ma, we put all those in. This one's negative because it's going backwards. 12 over 52 is 3/13 equals ma, and we just cancel out all the m's and solve for a, which is this. You could get a decimal, but I couldn't be bothered to type it in. Question number 7 then, we've got a picture here, a thing coming into this wall, hitting it, bouncing away, bouncing again. We've got loads of information here. The angle is between 0 and pi over 2, non-inclusive. I'll use that a little bit later. We have that the coefficient E between both walls is 2/3, so that's fine, we'll just jot that down. And I think we don't need any more of this text, really. We'll just go straight into here. Show tan of this is this. Now, earlier on in the paper, I just used that tan beta, if we call this angle of separation beta, and this beta as well, because of course alternate angles. I just used that tan beta over tan alpha is equal to E. Now, in a show that question, you're not allowed to use this. So if you just write this down and do it over here as well, you get to this very, very quickly. But we're not allowed to do that in a show that question. It's just really worth bearing in mind. If it says show that, you need to break these down into their components and then kind of get to this point on your own. So okay, let's do that. Let's break this down. If we call this speed here u, let's break this down into v sine alpha is there, and of course u sine beta is there. And then of course v cos alpha and u sine beta are across here in their components. That's good. And now what we are allowed to just use as fact is that in this kind of setup, the horizontal speed parallel to the wall doesn't change. So this is equal to that. And the speeds, the vertical component speed does change in accordance with E. So remember that rule we said earlier, speed of separation, which is essentially this vertically, over speed of approach, which is this, the approach that's coming into the wall, is equal to E. We rearrange that to say speed of separation equals E times speed of approach. So E lots of this is equal to that. Of course, E is 2/3, so I can put that in. And like I said, these two we can just say equal to each other. If we divide these, we'll get U's and V's cancelling, we'll get 2/3 tan alpha equals tan beta, sorry. And so this is where we're getting towards this, of course. So we've kind of shown this, but we also need to show it for this one over here as well. So we do exactly the same thing. Just jot down some components. If you call this W, I guess, this is going to be W sine beta and W, U, this is still on the U line, isn't it? So this is U sine beta, this is U cos beta, this is W cos of a half alpha, just written a half like this to squeeze it in, and here W sine of a half alpha. We can set up the same things. This is equal to this, this times E, because that's the approach this time, is equal to that. Put in the E value, of course, divide through, and we end up with this. But of course, that means I can write this as tan beta equals 3/2 tan of a half alpha, just by timesing this by 3/2 and then popping it in there. And we get this times by 2, divide by 3, we end up with this. I've also swapped the sides just to make it look a bit more like this. Now, where can I go from here? Well, at this point, I think I can just ignore this. I don't think we need it anymore. Just focusing on this bit, which is where I got to. How do we get this into this? Well, if we look in the formula book, we'll find not this, but we'll find the compound angle for tan in terms of A's and B's. If you just set A equal to B, you'll end up with this. And then, of course, we can replace 2 alpha with just alpha, which means replacing alpha with a half alpha, just dividing both these angles by 2, and we'll end up with this, which we can then just put into here, and we'll end up with that. Right? So just using the double angle identity there, and we'll get to this. And this is good because tan of a half alpha is not 0. Earlier it said that alpha was between 0 and pi over 2, not inclusive. So tan of a half alpha is not going to be 0. So we can actually just get rid of that, divide by it, get 1 equals to all this without this on the top. Times everything by 1 minus tan squared. And I think just 4/9 times 2 is 8/9. 1 minus 8/9 is 1/9 equals this. square root, and again, alpha being between 0 and pi over 2 means that tan is positive. So I don't need the minus a third here, and we'll show what we needed to show. Sorry for being lazy with these brackets here, I just stopped adding them for some reason. Anyway, I think I did too much work on this last bit. Yeah, so firstly what I did was I used this rule again to just find what the value of tan alpha is by shoving in tan over half alpha into here, and we eventually get the tan alpha as 3/4. Now if you imagine, of course, the 3, 4, 5 triangle, 4 as the opposite, 3 as the adjacent, that means, and the hypotenuse is of course 5, sine of alpha is going to be 4 over 5, and cos of alpha is going to be 3 over 5. Just good practice there, getting our trig values right there. So that's good. We can also, I guess, at this point, this is, some people will have noticed, or one person will have noticed that I uploaded this video and then immediately deleted it. The one person who had watched it before I did that 5 minutes later, because I noticed that thing that I said earlier about that you can't just use tan alpha over tan beta. That's what I did the first time, and I just after I uploaded the video, I read the mark scheme properly and saw that I couldn't do it. So I've uploaded again. So and then from here, I'm just doing what I did the first time. So that's why I've called these V1 and V2. So it doesn't matter. I've just changed what I'm calling this speed. So I used to call this U and W, didn't I? But who cares? So we have this same thing I talked about before, that E times this approach is equal to just that separation there. We know that E is 2/3, of course. We can say the same thing up here. So E times V1 sine beta is equal to V2 sine of half alpha. Now here, I know that tan over half alpha is 1/3, so we have a triangle with opposite side 1 adjacent 3. Now 3 squared times 1 plus 1 squared is 10, so the hypotenuse is root 10. So this makes up a 1, 3 root 10 triangle, and sine of a half alpha is going to be 1 over root 10, I think, if we just imagine that triangle ahead. So I can put that value in there. I can also put this, or I can't put this value in, I don't think, because I don't have it, but I do have that V1 sine beta is equal to EV sine alpha. So if I divide, what have I done here? I've divided this by E, it looks like, and then set it equal to that one, which means I can now just times by E again to get E squared over there, but I know sine alpha, I know sine of a half alpha, so I'll put those values in, and yeah, this is looking okay, I guess. E squared is 4/9. Rearrange all that in terms of V2, I guess, in terms of this speed. And that's useful because what I can now say is the kinetic energy at the start was just a half mv squared, of course, with this being V. So that's the kinetic energy before, ignore percent. This is just the kinetic energy before. And the kinetic energy afterwards is a half mv2 squared, which is just this thing squared. So I can do that and we'll get this. And this as a decimal is just 0.711, as I've said there. So just comparing these two things, everything matches except for this. So the kinetic energy afterwards, ignore this percent thing, like I said, is just 71.1% of what it was before because of this decimal multiplier, which means the reduction in percent is 28.8%. I think you could do that much faster based on the stuff that I did in part A, but it doesn't really matter. It's nice to just run through everything again and be clear about how we got everything. But yeah, you could certainly do that faster, I think. Anyway, that's the whole paper. Thank you so much for watching, and I will see you next time.